In this video, we're going to talk more about generalized coordinates, which we introduced in the last video, where we also introduced several very important concepts for the rest of the course. Essentially, we started with Newton's second law, and we found that by defining a quantity known as the Lagrangian as the difference between kinetic energy and potential energy, we could recast Newton's second law on this form, which is the Lagrange equation, or the Euler-Lagrange equation in variational calculus, which means that there's a functional with this definition, known as the action, that is stationary along the true path that the system takes when it evolves according to Newton's second law. We also said that we can make any variable change we like here. Right? The Lagrangian is the Lagrangian. It's here dependent on Cartesian coordinates, Cartesian position, Cartesian velocity, and time. But we could make a variable change so that it depends on some other set of coordinates, the corresponding velocities and time, given by this transformation. The action is still the same action. It will still be stationary in the same way. And that means that the Euler-Lagrange equation, known here and henceforth as the Lagrange equation simply, will look like this for the generalized coordinates. In other words, it doesn't matter whether you use Cartesian coordinates or some other more generalized coordinates to describe your system. The Lagrange equations look the same. Physically, I should say that this term here, the derivative of the Lagrangian with respect to position, that has the interpretation of force. And this derivative here, that has the interpretation of momentum. So that, to be specific, we have the force f of j equals the derivative, partial derivative of the Lagrangian with respect to position in the j direction, and the momentum is the same derivative, well, is the partial derivative with respect to the corresponding velocity. We can do the same thing for generalized coordinates. We can identify a force, although we're going to call this a generalized force, Q of j, capital Q of j, which is this derivative there. And similarly, we have a generalized momentum, which is the derivative with respect to the time derivative, the derivative of the Lagrangian with respect to the time derivative of the generalized coordinates, the L dq dot. Okay, now I'm calling these quantities generalized force and generalized momentum because they don't have to have the unit of force and momentum. This is because the generalized coordinates don't have to have the unit of position. For instance, if you're working in spherical coordinates, the coordinates you would have would be r, theta and phi. Theta and phi are unitless, and therefore the generalized forces and momenta would be different in those cases, and we'll see where that leads us in a minute. Before then, though, I'd like to issue one caveat. This is a very convenient formalism. You can change your coordinates. Physics looks the same, even if you're working in some very complicated coordinate systems. But you have to be careful. It turns out that Newton's second law is only valid, as we know, in the normal form in an inertial reference frame. And this is Newton's second law re-expressed, right, in a different form. And it wouldn't look like that if you were in a non-inertial reference frame. You can still make this change. Q sub I can still be describing a non-inertial reference frame, but you have to be very careful with the form that Lagrangian takes. It isn't so easy to write down t minus u correctly in a non-inertial reference frame. and you easily make a mistake. So therefore, I'm going to issue the following caveat. So we'll see later how this works when we solve some actual problems, but I'm mentioning it now because this is one of the main traps you can fall in when you do Lagrangian mechanics. Okay, so let's give an example here. It's been fairly abstract so far, but I'm going to give a particular example here that we've already seen. We're going to change our polar coordinates. We're going to change our coordinates into polar ones. So we're going to work in 2D polar coordinates. Okay, that's r and phi, of course. I should mention that earlier in the course we derived Newton's second law in polar coordinates, and I'm going to keep it here for reference. This is in chapter 1 in the book. We found that the force in the radial direction is m times r double dot minus r phi squared, and that phi sub f sub phi equals m times r phi double dot plus 2 r dot phi dot, right? So we'll keep that here for reference, and we'll access it later when we need it. Okay, we're now working in polar coordinates. So in order to write down the Lagrangian and the corresponding Lagrange equations, we need to first write down the kinetic energy and the potential energy, right? The Lagrangian, after all, is T minus U. So we'll start by writing down the kinetic energy. That's 1/2 mv squared. So that will be 1/2 times m, and then we have to write down the square of the velocity in the r direction. It's going to be r dot squared, and then we're going to add in the square of the velocity in the phi direction. That's r phi dot. Okay, hopefully you can see that. If not, we'll discuss that more in class, but this is something you should be able to write down right off the bat, that this is actually the velocity in the phi direction. Okay, and this is the velocity in the r direction. Alright, that's the kinetic energy. We're working here with a free particle, so I'm not going to write down what the form u has. U is just u, whatever it is. We know that u will depend, however, in general, on r and phi. So actually, I take back the fact that we're working with a free particle. We're not working with a free particle. We have a potential which can give rise to a force. Okay, so the Lagrangian, therefore, is equal to a function depends on r phi r dot phi dot. Doesn't depend on time in this case. So it is 1/2 m times r squared plus r squared phi dot squared minus u of r phi. Okay. Now we need to apply Lagrange's equation in the two directions. So we start out by the r direction. We have that dl over dr has to be d dt acting on dl dr dot, right? So we have the form here. We can see that this term depends on r, this term depends on r. So actually this should be a dot there. r dot, it's important. So what we get if we take the derivative with respect to r is mr phi dot squared, and then the derivative of minus u with respect to r, well, that's just f sub r, right? I should write that out explicitly. Du dr, but this is f sub r. And this now has to equal to the time derivative of the derivative of the Lagrangian with respect to the velocity, and that's just mr dot. So this becomes mr double dot because the mass is constant. So we end up then with f of r equals m, if we move this over on the other side, right? M times r phi dot squared. Well, need a minus sign there. So it's m r double dot minus r phi dot squared. Okay. So that is so far so good. That's the same form that we got using more geometric methods earlier. Okay, now let's take a look at what's happening in the phi direction. And once we've written down the Lagrangian here, we don't actually have to care anything more about what the geometry of the coordinate system looks like or anything. We just write down the Lagrange equation. So it has exactly the same form for phi as it does for r. dl d phi equals dt acts on dl d phi dot. So now we have to look at this. Okay, the only thing that actually depends on phi here is the potential. So this becomes minus du d phi. Now, du d phi, it turns out, is not actually the force in the phi direction. This is not equal to f sub phi. We can tell that because f sub r will not have the same unit if it did, right? Here we have the u dr, it has the unit of energy divided by position. This just has the unit of energy. So this is not a force. So we have to do a little bit more work in order to relate this to a force, but not too complicated. So let's remember that we're working in polar coordinates, and then we know that the force is minus the gradient of u. So in polar coordinates, in two-dimensional polar coordinates, the gradient is minus the u dr r hat. The minus sign carries over, right? And then we have to add in the phi term, which is 1 over r du d phi phi hat. Then everything has the same unit. So we get then that f sub phi is minus 1 over r du d phi, or that r times f sub phi equals minus du d phi. All right, so now we have what we need in order to proceed. So this now is very clearly equal to r times f sub phi. Okay, but we have to proceed here and calculate this derivative as well. So we have d dt acting on the L d phi dot. So here's the Lagrangian. We will then get that that is equal to m r squared phi dot. And then we now need to simply calculate the time derivative with respect to this. This is a full derivative, and both r and phi depend on time. And both r and phi depend on time. So this then becomes equal to 2 m r dot r phi dot plus m r squared phi double dot. All right, So we can take the m out in front, so this becomes then m times 2 r dot r phi dot plus r squared phi double dot. Now we can simplify this. We just get rid of these r terms here, and we end up with a final result that f sub phi equals m times 2 r dot phi dot plus r phi double dot. Okay, aside from the order of the terms, which doesn't matter, this is the same result that we found up here. So we have found the expression for Newton's second law in polar coordinates in the same way that we found it, well, in a different way from the way we did it in the beginning of the course, except that now it was really much easier. The only thing that required any kind of thinking, really, once you have this down, is the notion that the velocity in the phi direction is equals to r times phi dot. That's the only quasi-geometric concern you have to do. After that, all you do is just apply mechanistically Lagrange's equations. You have to, of course, come up with that du de phi is actually r times phi sub f sub phi, but that follows directly from the definition of the gradient in polar coordinates, which you can easily look up, and then you arrive at this result. So this is definitely a simpler approach to working in curvilinear coordinate systems than just applying Newton's second law in its regular form. The other thing I want to discuss here is the meaning of the generalized force and generalized torque in the generalized, I gave it away there, generalized force and generalized momentum in this system. Okay, so let's look at the generalized force first. Generalized force is the L de phi, that's r times f sub phi. By the way, if we were to do this in the r direction, we wouldn't find anything very interesting. The force in the r direction is the L d r, and the L d r dot is the momentum in the r direction. But here we find something slightly different. This generalized force does not have the unit of force. It is distance times force, and this force is actually in the direction perpendicular to r. So let's draw a little picture here. We're sitting here. This is r. And this is the direction of f sub phi. Phi hat, well, actually minus with that. And this is a right angle. So actually, this, it turns out, is equal to the magnitude of r cross f. You should be able to see that relatively easily. It is equal to the torque. So the generalized force in this case, for the phi variable, is torque. And you already probably know that torque is the rotational analog of force, but here it falls out very naturally from Lagrange's equation. So let's see what we get then for the generalized momentum. So the L d phi dot. Well, we already calculated that. That's m r squared times phi dot. So m r squared, well, that is the moment of inertia of this particle here of mass m. Phi dot is the angular velocity of that particle. So this is I omega. In other words, the angular momentum. So what we find, and you should already know that angular momentum is the rotational analog of regular momentum. So if we then look at this equation here, it actually turns out that this is directly equivalent to, okay, this is the torque, gamma, equals the time derivative of angular momentum, so that's L dot. So this is Newton's second law for rotation. And that comes out completely naturally. We don't have to do anything special to derive it. Think about the rotational case as anything different from the linear case. It simply falls directly out of the equations, which is quite neat. Okay, we'll end this video here. In the next video, we're going to talk first about multiple particles, because we're often looking at more complicated systems. And then we'll also begin to treat constrained systems, which is a very important case.